Should be
Jordan, you are giving consent to this meeting to be recorded. They know where I am.
All right. Ready?
Yeah.
All right. So today we're going to look at the examination of network dynamics using random walks. I'm Nayo Ogilvie.
I'm Peter Larsen.
All right. So what we're going to go over for this presentation is we'll start off by, telling you a little bit about what we're going to be modeling, how we modeled it, the results that we've gotten so far, and then further steps over the next few days before the deadline next week. All right, so what are we modeling? We're basically modeling three separate parts, but part one is going to be comparisons using random walks between a standard 3D space and a non-uniform dimensional network. In the second part, we'll start discussing the random walk of the non-uniform dimensional network with specific origins based on centralities. And then finally, we'll look at navigating a network with random walks while including bias for paired networks. All right, so part one, how is it being modeled? So basically what we've done is we've created a network of Marvel comics, and we're using the characters within that, within the universe to create an adjacency matrix and linear, and using that adjacency matrix and linear algebra manipulations to create that network. So we've got two pictures below that have the graphical representations of the person-to-person network of the characters within this universe. So the first one here is display using the Python package network X. In this case, each node represents a different character, and the edges represent the connection between those two characters. Next, we have the Gephi representation of that, where it's hard to see in this image, but there's the names of all of those characters that interact with each other. And the colors within this represent the different groups that they're a part of. All right, so how is this being modeled? So for part one, we basically start with a random node from that network that you saw above. And from that random node, we randomly move to a neighboring node. And we perform this movement 1,000 times. And then we perform those 1,000 movements over 100 different iterations to kind of average out all the results and smooth out irregularities. So in this case, we also use non-uni for non-uniform dimension and degree, which you'll see throughout the rest of this presentation. On the right here, you can see a random walk through the nodes. The red indicates where the walk has occurred. In this case, it's after 100 time steps, not the 1,000. It's just with 1,000 times, 1,000 steps, it looks very confusing. So 100 is a little easier to see. So to compare that to our standard 3D random walk, we had just a standard XYZ coordinate plane where we mapped out, stepping in a direction 1,000 different times. And once again, to smooth over irregularities, we iterated it, we performed that task 100 times and averaged all results. In this case, we denoted this as our uniform dimensional degree, which you'll see later in the results. So Peter's going to take over for results.
Yeah. In order to compare the uni and non-uni random walks, we implemented two metrics. Coverage fraction, denoted as CF, which measures the amount of unique nodes visited by each run, and rate of return, being ROR, which measures the overall success of the random walk returning to its origin at some point within its run. Mathematically, we are able to calculate the probability of the rate of return for a standard 3D random network. This was done with a combination of 6 or 7 people listed on the screen, but it's about 34% likelihood that a 3D random walk will return to its origin at some point. So the coverage fraction for the uni runs was 67.41%. The coverage fraction for the non-uni runs was 73.13%. That means that on average, the random walk in the P2P network was reaching approximately 50% more unique nodes per run than the 3D random walk. The rate of return for the uni runs was 34%, which was fantastic. It means that it matched up exactly with the mathematics as it should. And the rate of return for the non-uni runs was 44%. That means that aside from our results, it means that a non-uni run was 10% more likely to return to the origin at some point within 1,000 time steps. Now, this is potentially due to the fact that the non-uni network is a closed network, and so there is no possibility of escape. Whereas the uni technically has an infinite edge. The edge is an infinite distance away, and so you can continue to go away. There is a bounded limit in the non-uni. So on the screen now is a graphical representation of the 100 runs. The blue represents the number of unique nodes visited for the uni runs, and the orange represents the number of unique nodes visited for the non-uni runs. So as we can see, the uni runs were more spread out over a wider range, and the non-uni runs are very highly clustered in towards that high end, over 700 unique nodes visited of 1,001 possible nodes to visit. So that suggests that we aren't necessarily seeing trapping as we might expect. The odds of return make it so that you are less likely to be in the same place. And so therefore you're going to reach more nodes. We can go to the slide. Yep. So part two, how we modeled it, is instead of starting at a random node in the P2P network, we started a pre-selected node and then go about the same actions. And we will discuss that pre-selected criteria in the next few slides. But again, it's, yes. So the nodes in the P2P network were selected based on their centrality scores in three different measures: betweenness centrality, closeness centrality, and eigenvector centrality. Betweenness centrality is essentially a measure of how central a node is on the path between any two nodes. Closeness centrality is the measure of the average distance from a node to every other node in the network, where distance is defined as path length. And then eigenvector centrality is a score based on your neighbors being central in themselves. So the more central your friends are, the more central you are. Yeah. So we looked at essentially the top five for each centrality, the middle five for each centrality, and the bottom five for each centrality. So the average coverage fraction for the top five was 72.9% for betweenness. The middle five was 73.2, and the bottom five was 72.48. Now, this is very interesting, if you go back, in that the highest percentage is actually the middle. And so that's just something to think about. It's an interesting thing to note. Why would that be? We're not sure. That requires further investigation. Okay, for the eigenvector, the top five is 73.56, the middle five is 73.306, and the bottom five is 73.366. So here, the bottom five are actually better at covering or visiting more unique nodes than the middle 5. However, the top 5 is better than the other 2. And this is, what we might expect in terms of the top 5 being better, because they are more central to other central people. And so they're able to reach wider networks within the network as a whole. They can reach more substructures, ideally. And then lastly, we have the closeness centrality. And so here, this is the first of the 3 that actually has the top 5 is greater than the middle 5 is greater than the bottom 5. And this might be due to the fact that closeness is a relatively simple calculation. All it is 1 over the sum of the distances between that node and every other node, where distance, again, is path length, shortest path length. And so the top 5 closeness average is 73.566, the middle 5 is 72.8, and the bottom 5 is 72.5. This, again, like I was saying, is the first that is properly tiered, going from top to bottom. We aren't sure why, and if you continue on now, the reasons that we haven't done the 100 iterations for each of the specific nodes in the top 5, middle 5, and bottom 5 for all 3. And so we aren't sure necessarily if these numbers are outliers or if they are true to the norm. And so this requires further work. We hope to get that within the next week or so. And then part 3. So part 3, we are trying to use weights from another network that is paired with the P2P network, in that we began with a bipartite matrix of people to groups. That matrix can then be multiplied in either the form A transpose, or A transpose A. One of those gives the person-to-person network that we've been discussing above. The other gives group-to-group, or G2G. And it shows the amount of people shared between various groups in the Marvel Universe. So the idea with part 3 is, can we use those weights in the G2G network to influence the adjacency lists of the nodes in the P2P network to try and go from a target group, or from an origin group to a target group. So the idea along that is you designate a random group as the origin, and you designate a random group that isn't your origin as your target. You then select a random member of your origin group such that they are not a part of the target group, and you take their adjacency list. An example would be node A is adjacent to B, C, D, E, and Z. And then we use the group-to-group network to look for our target group R and B, C, D, E, and Z's relationship with group R. So B to R might have a 5, C to R might have an 11, D to R might have a 1, E to R might have a 0, and Z to R might have an 8. Then you alter the adjacency list such that each of those entries is now weighted according to their weights from the group-to-group network. And then you randomly choose from that new adjacency list. So now before, where you had an equal shot of going B, C, D, E, or Z, you now have a higher likelihood of going to C, then a greater likelihood of going to Z, but that is also greater than B, and then that is greater than D, and then E is completely removed. We are trying to avoid going to E, as E has no connections to our target group. So we are forcing the bias into the adjacency lists, and then repeat from our new node. We have not been able to implement this yet. We are in the process of coding this properly. Multiple CSVs are trying to be worked in, and that is where our hangups are currently.
All right, so to wrap up, we've created a network based on the Marvel comic characters using an adjacency matrix and linear algebra manipulations. In part one, we've wrapped up. We've implemented, tested the random walks for the uni and non-uni networks. Part two, we've also implemented and tested. We do want to do a little bit more work to get more iterations to make sure that our results are more conclusive. And then finally, part three, we've started implementing the model, but we haven't quite finished yet, so we will have results shortly. And that is the end of our talk.